Okay, welcome to the second video where we're going to take a look at some of the possible mandatory experiments that might come up in question 1 of this year's exam. So previously we looked at the ethanoic acid titration. Here we're going to take a look at a redox titration, mandatory experiment 8.4, where we use a solution of iodine, a standardized solution of iodine to standardize a solution of sodium thiosulphate. Okay, let's jump into some of the more general aspects of it first of all. So sodium thiosulphate is usually in crystal form, okay, something like this, okay, and you can see that this is not a primary standard because, of course, it has water of crystallization. So when we weigh this out and make up a solution from it, we have no way of knowing the exact concentration. It's not a primary standard. Make sure you remember that definition for a question like this. It's likely to be asked somewhere there. It has been before. So primary standard is something that's in pure stable form that can be used to make up a solution of known concentration. The thiosulphate itself is a reducing agent, and so in the reaction, it itself will be oxidized. This is the reaction here. Not something you need to remember exactly. You'll be given the full equation in the exam, so you'll be able to pull this part out of it. Okay, but very important that it's not a primary standard. Why? Well, the water of crystallization is probably the easiest thing to remember since you'll be given this formula in the exam. Iodine, on the other hand, is a halogen. So like all halogens, it's going to be an oxidizing agent. So it itself will be reduced then in the exam, in the reaction. Okay, here's the reaction for the reduction of iodine. So since it's diatomic, it'll contain 2 iodine atoms. Okay, when these are reduced, it'll form 2 iodide ions. So of course we need 2 electrons to balance that equation. Okay, it's not a primary standard either. Why not? Well, iodine being diatomic is not very soluble in a polar solvent like water. So it's not going to be very soluble because of that. But also it's not a primary standard because it sublimes even at room temperature. So as soon as you start to weigh it out, some of it is evaporating off. So you can't know for sure how much you're actually weighing out. So it's not a primary standard. You can't create a standard solution from it. Okay, right. Let's take a look at the how we make up our standard solution of iodine. Since it's not a primary standard and we're using it to standardize the thiosulphate in this reaction, of course, then the iodine must have been previously standardized in some way. So how do we standardize our solution of iodine? Now, for any questions related to this, really what they're going to be looking for is bringing it in contact with iodide ions. Okay? Iodide ions, usually in the form of potassium iodide, Ki. Okay? So when iodide comes in contact with iodide ions, it'll form triiodide ions, okay, these I3-. Now, these are chemically identical to iodine. They react in the exact same way, but they're much more soluble because, of course, of the charge, okay? So this reaction here will increase the solubility of iodine, okay? And this is a very common question in any iodometric titrations. They ask about how can you increase the solubility of iodine? How can you get the iodine to stay in the solution? So you have excess iodide ions present, or excess potassium iodide. Okay, we can then make up our standard solution based on that, and we can use that to titrate against the thiosulphate. Now, this second box here is probably not something you need to desperately know for this titration. It's really a guide to how you would make up a standardized, another way to make up a standard iodine solution. Okay, and largely in the video when we went through this, it was really to kind of make prepare you for the next video on the bleach titration, where we use something very similar to this. But in this titration, it's probably not something we need to worry about. But either way, we get an iodine that we can use to standardize our thiosulphate. Okay, let's take a look at the reaction between the two. Now, you'll be given this in the equation, in the exam, so this is not something you need to remember. But keep an eye on the oxidation numbers. Make sure you're comfortable with assigning these. The oxidation number of sulfur goes from +2 to +2.5. Something like that could be asked. It generally isn't, and they haven't really ever asked about oxidation numbers before. It usually come up in question 10 or 11, but it's possible. Now, very important though is the end point of an iodometric titration. Okay, so like we've said before, with redox titrations, they don't generally need an indicator because, of course, as they change oxidation number, they tend to change color, and that tends to act as an indicator themselves. So we say that they're their own indicators. This isn't the case in an iodometric titration, however, where we have iodine, because iodine will start off with this kind of color, okay, this kind of wine red color. And as we go through our titration, this color will become much more faded as the concentration of the iodine decreases. And it becomes a yellow, and this yellow becomes paler and paler and paler. Often we refer to it as a straw yellow, okay? And it happens so gradually that the endpoint is not obvious. So you don't know when to stop the titration. So you don't have an accurate titer, okay? The solution, of course, is to add starch, okay? When we add our starch, it turns the solution blue-black. So we wait until it's a very, very faded yellow, add some starch, we get this blue-black solution. And then when we continue with our titration, the transition from blue-black to colorless is very dramatic, and that allows us to accurately measure our titer. Okay, moving on to a question then. This question is from 2007. But before I look at the question, another thing that's very commonly asked in this question is the making up of the sodium thiosulphate solution, okay, and the steps involved. They'd often ask you to describe this procedure. So you're going to weigh out your crystals. Again, it's not a primary standard, so we really don't know how much thiosulphate we're actually weighing because of this water of crystallization, but we'll weigh it out, transfer it. Here you see there's no reading because we're not even given in this question the amount that we weighed out. So we transfer it to a volumetric flask. Sorry, we don't transfer it to a volumetric flask. So the whole steps, you'll transfer this to a beaker. You'll wash it into a beaker, and you'll wash the clock glass. Then you'll use a stir bar to try and dissolve it all. And then you'll transfer that to a volumetric flask. You'll wash the stir bar, you'll wash the beaker, you'll wash everything that the solution came in contact with to make sure that every last drop goes into the volumetric flask. And any drops left behind, you are sure that they are just deionized water. You'll bring the solution up to close to the mark with the wash bottle, and then the dropper will bring the bottom lemniscus up to the mark. So basically the procedure that we had in mandatory experiment 7.1, where we described the making up a standard solution of sodium carbonate. So it's essentially those steps, but that this will come up. It has done. Anytime this question has been asked previously, they've asked you to list the steps in making up the sodium thiosulphate solution. So make sure you're clear on those points. Okay, as for the question here, let's take a quick look. So we're told that we weigh out a certain mass. So we're not actually told what this is. We're told it's into 500 centimeters cubed. And then it's titrated against 0.05 molar iodine. And we're told that the titer was 20 centimeters cubed. And we're asked to find the molarity of the sodium thiosulphate solution. So moles per liter. And we're also asked to find its concentration in grams per liter. Okay. So basically, what was the concentration in this volumetric flask? Okay. Now, the thiosulphate will be in the burette. Okay, so when we are given the titer here, this is the volume of the thiosulphate. So be careful, students often get confused with this, okay? The iodine is going to be in the conical flask. It's not colored here because, of course, this is showing us the endpoint of the titration when it has changed to colorless, okay? You can see that we have our average titer here. So this is the titer we're given in the question, 20 centimeters cubed. And that reacted with 25 centimeters cubed of my iodine. And this iodine is 0.05 molar. Okay, so we have enough information about the iodine to work out how many moles of iodine reacted. So that's going to be the volume, 25, times the molarity, 0.05, give us our 0.00125 moles of iodine. Now, when we check our equation, it's a ratio of 1:2. So we will have twice that number of moles of thiosulphate, so 0.0025 moles. And this will allow us to work out the concentration of the thiosulphate, because here we have the number of moles and we have the titer, of course, 20 centimeters cubed. Okay, so we can get the molarity by rearranging this equation. It's going to be 1,000 times the moles over the volume, and it gives us 0.0125 moles per liter. Okay, that's the answer to the first part. Now we want to find out the concentration in grams per liter. Now be very careful of the wording here. Okay, here it says grams of crystal. Okay, crystal means the whole thing. They could just as easily have asked in this question the mass of sodium thiosulphate, which would be just this. Now this is important because, of course, now we're dealing with mass. So we're going to be multiplying by the molecular mass. So we need to know which number we're going to be using to multiply by our molarity. Okay, here we're asked for crystals. So we're going to take the molecular mass of this whole thing, which is 248. So it's written here. So it's the molecular mass of this Na2S2O3.5H2O. Okay, so that's 248. Multiply by that, we get 31 grams per liter. That's our answer to part B. But of course, if they just asked for sodium thiosulphate, then you would have to ignore this water of crystallization. This would be irrelevant, okay? And you'd be just looking for this. So you'd be multiplying by the molecular mass of that grams. Okay. And that's pretty much it. I don't think there's anything else pertinent. Maybe sometimes they've asked questions about using deionized water versus distilled water and doing some things. I think that's come up previously with this titration. So if there's any question like that, why it's always better in any kind of redox titration to use distilled water rather than deionized water, because of course deionized water just has ions removed, whereas distilled water is absolutely pure water. It has everything removed. So there still could be some substances in deionized water which are not ions that could affect the titration. And the most prominent example would be a halogen like chlorine. If there was some chlorine in the deionized water, it wouldn't have been removed because, of course, it's not an ion. And chlorine is an oxidizing agent. So if there's any traces of chlorine, that would affect our end result. Okay? But you'd probably be safe enough to just say any non-ionic or any maybe organic substances that could interfere with the reaction. Okay? But chlorine is the easiest example to remember because, of course, it's like iodine. It's an oxidizing agent. And it's not going to be removed from a deionized water. Okay, hope that helps. And keep tuning in for the rest of these videos as we go through the rest of the mandatory experiments. Okay, thank you.